Imagine a world where energy flows smoothly, like water from a tap. That was the prevailing belief in physics at the turn of the 20th century. Then came Max Planck, a German physicist, who dared to challenge this classical view.
In 1900, while studying the radiation emitted by heated objects, I stumbled upon a revolutionary idea. Energy is not continuous, but rather exists in discrete packets, or quanta. This radical concept, known as energy quantization, marked the birth of quantum mechanics.
Planck proposed that the energy of each quantum is directly proportional to the frequency of the radiation. The higher the frequency, the greater the energy of each quantum. This relationship is expressed by Planck's famous equation, E equals hn, where E is energy, nu is frequency, and h is a fundamental constant now known as Planck's constant.
My discovery initially met with skepticism. It contradicted the established laws of physics, which assumed energy to be continuous. However, my theory elegantly explained the observed spectrum of black body radiation, a phenomenon that had puzzled physicists for years. This groundbreaking work earned me the Nobel Prize in Physics in 1918 and laid the foundation for the quantum revolution.
Imagine a packet of light, a tiny bundle of energy, carrying a specific amount of energy. That's a quantum. It's the smallest possible amount of energy that can exist for a given frequency of light. Think of it like this. You can't have half a photon or a quarter of a photon, you can only have whole numbers of photons. Planck's constant, denoted by the letter h, is a fundamental constant in physics. It relates the energy of a photon to its frequency. Think of it as the exchange rate between the energy of a photon and its frequency. The value of Planck's constant is extremely small, approximately 6.626 times 10 to the power of negative 34 joule seconds. This tiny value highlights the quantized nature of energy at the atomic and subatomic levels. The concept of the quantum revolutionized our understanding of energy. It's like discovering that money, which we perceive as continuous, is actually made up of discrete cents. This quantization of energy has profound implications for our understanding of the universe, from the behavior of atoms to the nature of light itself. Albert Einstein, a young physicist at the time, was deeply intrigued by Planck's work. In 1905, Einstein took Planck's quantum hypothesis a step further.
I proposed that light itself is quantized, consisting of discrete packets of energy called photons. I used this idea to explain the photoelectric effect, a phenomenon where light shining on a metal surface causes electrons to be emitted. The classical wave theory of light couldn't explain why this effect only occurred at certain frequencies.
Einstein showed that the energy of a photon is directly proportional to its frequency. If the frequency is high enough, a single photon can have enough energy to knock an electron loose from the metal.
My explanation of the photoelectric effect cemented the validity of Planck's quantum hypothesis and earned me the Nobel Prize in Physics in 1921. My work revolutionized our understanding of the nature of light and paved the way for the development of quantum mechanics.
For centuries, scientists debated the nature of light. Is it a wave spreading out like ripples on a pond? Or is it a stream of particles like tiny bullets of energy? The answer, surprisingly, is both. Light exhibits a wave-particle duality, meaning it behaves like a wave in some experiments and like a particle in others. The wave nature of light is evident in phenomena such as interference and diffraction, where light waves interact with each other, creating patterns of bright and dark regions. On the other hand, the particle nature of light is demonstrated by the photoelectric effect, where light interacts with matter as discrete packets of energy. This duality, while initially perplexing, is a fundamental concept in quantum mechanics. It suggests that our classical notions of wave and particle are merely approximations of a more complex quantum reality.